Hello everybody. Today in this experiment we will first construct our simple voltage divider circuit, which consists of 1 kilo ohm resistor and a series light dependent resistor. So we plug them in. So I tilt the LDR into one side so that it can measure distance horizontally, and I tilt it to the window side so my equipment won't be in the way. My equipment and cables won't be in the way of the LDR. I plug in my DC power supply, which is configured to be 12 volts, and output current is limited to 100 milliamps of current each. So I plug my I connect my DC multimeter probes to the terminals of the LDR, and then I will take measurements from various distances and write down the voltages. I am using my phone's flashlight as a light source, and as you can see there is a voltage reading when I'm very far, and when I'm at 90 centimeters I get another voltage. Then I repeat them for 60 centimeters, 30 centimeters, 15 centimeters, and then 10 centimeters, 5 centimeters, 3 centimeters, and then 1 centimeter. Then I write down those and plot them in Excel, and then I construct my other circuit, which we just use an op-amp as a basic comparator, and use a signal generator to compare the voltage of the LDR and get a PWM output signal, which we will inspect. First I connect my power rails to the op-amp, which are plus and minus 12 volts with respect to ground. I limit the output current also to 100 milliamps. Then I convert the inverting input to the voltage of the LDR, the positive side of the LDR, and then non-inverting input, I connect the non-inverting input to the signal generator, and I connect the signal generator's ground to the common ground. Then I hook up my probes. I hook up the channel 2 to the output of the op-amp. Then I hook up the channel 1 probe to the output of the signal generator. As you can see, I'm connecting all the grounds to the same connections. Now as you can see, here are my voltage recordings, different voltages with respect to different centimeters. These values might be different from the what you saw in the first part of the video. This is because we did these procedures, the test procedures, in a different day with different lightings. So we did the whole calibration step all over again. So here are my values. I set 100 centimeter to 20 milliseconds. Then I use this equation to assign a millisecond value to each distance value. So 90 centimeter would be 18 milliseconds, 60 would be 12, 30 would be 6, 15 would be 3, 10 would be 2, 5 would be 1, 3 would be 0.6, and 1 would be 0.2. Then I use my values, millisecond and voltage values, to set up an arbitrary waveform, generate an arbitrary waveform from the signal generator. To do this, I will push the ARB button, arbitrary wave button, at the signal generator. Then I will do, if you don't see any waveforms, you can just press create waveform. Then I will select my cycle period to 20 milliseconds. Then I would do the high V to my ambient reading, voltage reading, then and low to do 0. And then I will set my zero initial point to 0 centimeters, 0 volts at 0 milliseconds. Then I press insert point every time I define a new value. So for the first point, I select the time as 0.2 and the voltage value as 0.49 as I measured in the first step. Then I do the following. I do the same for the rest of the points. So as you can see, I fast forward a bit, This process takes a bit amount of time and getting used to. So in reality, this process took me about 5 minutes. So I save my waveform as an arbitrary waveform, and then if we open up the output, and we can see in the oscilloscope the waveform that we just configured, and we can see the milliseconds in the x-axis as time and voltage values at the y-axis. And so we just it is the same as the Excel plot that we obtained earlier. So if we look at the output, as we bring the light source closer to the LDR, we see that the output waveform is getting slimmer and slimmer. So the duty cycle of the PWM signal is getting lower and lower, and by theory it should the duty cycle should vary with distance linearly. So as you can see, the output waveform is changing as expected. So I put the phone to an arbitrary position, and then I read the plus width of the output waveform, and then do the necessary calculations. So I put my phone to the with a distance of 26 centimeters. So using the beforehand of equation, we can see that if we multiply the plus width time by 5, we get the distance in centimeters. Also, the time needs to be in milliseconds in order for this equation to work. So we measure the plus width at 26 centimeters. Let me bring my camera closer. So around 5.7 milliseconds. If we multiply this value by 5.8, we get 29 centimeters. So this is a bit close. Now we test again from an arbitrary distance. So I put my phone like that, and then I measure the distance, and then I look at the output waveform and the plus width, and I see that it's 10.4 or 5 milliseconds. Then I multiply this value by 5 to get the centimeters, distance in centimeters, and this turns out to be 52 centimeters. But I actually put my phone at 42 centimeters away, so there's a huge margin of error there, like around 11% of error there. So I bring my phone closer to test from a closer range. As we can see, the plus width of the output waveform is 4.5 or 4.6 milliseconds. If I again do the same calculation, so I measured my phone's distance as 20 centimeters, and I get a value of 23 centimeters, so the margin of error is less. Now I bring my phone even closer. I get a value of 1.73 or 2. I do the same calculations. I have put my phone at 8 centimeters away, and the calculated distance is, if I use my calculator here, I get a rough estimate of 8.7 centimeters, which is even closer prediction. As we can see, in closer distances the sensor acts better, but in longer range the sensor can guess, but the measured values are more erroneous than measurements done in closer range.